Welcome back, part 3 of Time in Geology. An index fossil, again, is something that lived widely across the planet. It was relatively short-lived. Now, for geologists, that means a few million years at most. And it's recognizable. If it looks like everything else, it's not going to be a good index fossil. When we find a trilobite, we know that the rock has to be of a certain age. This is from The Onion again. The tiny trilobite just evolving away without a care in the world. Evolution going great, reports trilobite. And you can pause and read that. It's kind of fun. The Onion is always kind of fun. Here is a bed with a different species of trilobite. I want to say this is the, it's not the Flexocalamine. This is the Phacops rana trilobite. Yeah, all the species have different names. And I forget how many millions of years old this is. Now, here are some index fossils. If you find a rock with these particular types of fossils in them, you will be able to identify how old the rock is. Now, I know this looks like things that you might find in the ocean today, but there are some subtle differences. These things change over time. By the way, notice here are trilobites. Then after about this time, you never find them anymore. They start changing into something like this, and then they're gone. Okay, here are a few more sequences. You're welcome to try these out. I will put one or two of these on your test, and you're going to have to figure out which is the youngest and which is the oldest. I think I will stick this in your chapter as a fun little activity. Now, absolute age and the geologic time scale. Scientists have developed the geologic time scale, going from the earliest part of the Earth to the most recent part of the Earth. Anything before Cambrian is called Precambrian. So the earliest part of the Earth, from about 4.55 billion years ago to about 544 million years ago, it's all called Precambrian. Why don't we know a heck of a lot about it? It's been heavily overturned, heated, melted, squished. A lot of this is metamorphic rock. Now, this is the geologic era called the Precambrian. We break it down into sub-eras or epochs called Proterozoic, Archean, and Petarchan. You're never going to use that word. Then comes, this is weird. Your book is making things a little bit weird here. This is Precambrian, then comes Paleozoic, and then Mesozoic, and then Cenozoic. This is how long Precambrian lasted. Notice the break in here? That indicates we're missing something. Paleozoic was where the Earth was mostly water. Mesozoic, you think of it as the age of reptiles. And Cenozoic, we think of the age of mammals. This is the entire geologic sequence, and these colors are standardized. When you take a geology class in college, you're going to be using this type of stuff. Here are the millions of years ago before present. And then again, each area here is broken down into little epochs or sub-time periods. We are living in the Holocene epoch of the Cenozoic era, which came before the Mesozoic era, which came before the Paleozoic era, which came before after Precambrian. Now, if you want to compress geologic time into 1 year, this is one way to do it. Pause here if you want to look at it. I don't want to run through it, but it's kind of cool. If you want to compress geologic time into a highway, this is kind of cool. Here's the beginning. Here's the end. Don't ask me why they ended at New York. Ooh. Sorry, New Yorkers. But here's the start. Everything all the way up to here, Pittsburgh, is Precambrian. The oldest rock we can find is here. We can find abundant marine fossils right about here. So this then is the Paleozoic era. Then this becomes the Mesozoic era. And then this becomes the era Cenozoic. And we get to New York City. When we get to one street, the Ice Age ended about the last 10 meters of this trip. 2,000 years ago was the sidewalk, and a human lifetime is about 1/10 of 1 meter. Kind of sad. Again, here's a geologic time scale. You can find these things all over. Now, how can we really date rock? Not just relatively, but figure out the age? we use what's called radioactive decay. Thankfully, radioactive materials break down at a constant rate. There are three types of radioactive decay that we use. Alpha decay. In alpha decay, 2 protons and 2 neutrons are lost, essentially a helium nucleus. This will set off a Geiger counter. And this is pretty damaging stuff if it gets in your lungs. The good news is it's pretty massive and it can be stopped. Beta particles, just an electron. And gamma radiation, oh, they left that out. But here we go. Uranium-238 over time breaks down into lead-206. It doesn't do it all in one step. Uranium-238 gives off an alpha particle and becomes thorium-234, then a beta particle to become palladium-234, then back to uranium, then another alpha decay. Notice it's dropping 4 parts every time here to go to thorium, radium, radon, polonium, and then lead. And this is a radioactive lead. It's unstable, so it keeps giving off pieces of itself. But in this case, it goes through 2 beta decays through bismuth, polonium. Polonium then gives off 4 of its pieces. 2 of those are protons and 2 of those are neutrons, so it becomes a lead-210, still radioactive, which breaks down into bismuth-210, different from bismuth-214, then polonium-210, and then lead-206. How long does it take uranium-238 to break down to 206? Well, for half of it to break down, takes about, total time, where did we go? Uranium-238, 4.5 billion years for that entire thing to happen. So if you have, let's say, 24 ounces of uranium, and you wait 4.5 billion years, you come back and test it, after 4.5 billion years, 12 ounces will still be uranium, 12 ounces will be lead-206. What will happen after another 4.5 billion years? Well, remember the 12 ounces that you had that were still uranium? Half of that will decay into lead. So you then will have 6 ounces of uranium and 18 ounces of lead. What happens if we wait another 4.5 billion years? Oh man, this is getting tough. There will be 3 ounces of uranium left, and the remaining 21 ounces will be lead. You get the idea. Now, what happens is your original product, the parent isotope, goes down over what are called half-lives. Here's 4.5 billion years, 4.5 billion years, 4.5 billion years. The daughter product, the thing it breaks down into, increases. But you can see what happens. After a few half-lives, the original product becomes very little, so we can't measure this after so many half-lives. All these dark dots are the uranium-238. Drops down to here, 1/4, 1/8, 1/16 the amount. Really, 1/2, 1/4, 1/8, 1/16. The next step would be 1/32. We could do the same thing with a candle, but a candle's different. A candle burns at a steady rate. It's not geometric. Candles, it just doesn't work. Now, we use different isotopes for different fossils of different ages. For example, if you're dating something really old, you want to use U-238. If you want to use something a little bit less old, you're going to use potassium-40. Uranium-235, less than 1 billion years. And carbon-14, found in a lot of living things. This little graphic says we can date things anywhere from 100 to 40,000. I believe they've stretched it up to about 70 to 80,000 years. But after that, there's too little carbon-14 left. It is broken down into carbon-12, and we can't use it anymore. Now, can we combine relative and absolute ages? Absolutely. By looking at the isotopes in these rocks, not only can we put everything in order, but we can establish the actual age of these rocks. Take a look. This granite is somewhere around 540 million years old. What does that tell us? Well, if the granite intruded into this Birkeland Formation, we know the Birkeland Formation has to be older than that. Not only that, this unconformity has to be older than 540 million years old. This dike cut across the granite and this area, so we know it's younger than the granite, younger than this unconformity, but younger than the Foster City Formation. By using radiometric dating, we can find out it is 78 million years old. This is kind of cool stuff. And I think that is it, folks. That's the end of part 3. Enjoy the chapter. This is really cool stuff. And be ready for a few of those drawings in the test. If you have any questions, write me.